Hi guys, Rod from Bensonian Thought Videos here, and this is the second video in my series examining the underlying philosophy that gives rise to the scientific method. So in last video I argued that the scientific method itself operates under at least four presuppositions or axioms and also relies on two important intellectual tools. The four axioms or presuppositions of science I presented all started with the letter C, and these were coexistence, coherence, correspondence, and conservation. Last week we covered the first two, coexistence and coherence. To very briefly recap, coexistence is the idea that there is a universe that coexists with our consciousness and which is independent of our own existence and about which our bodily senses give reliable information. The coherence axiom was to do with the simple laws of logic, and we examined this in relation to the famous Descartes statement, "I think, therefore I am." In summary, for a scientific theory to be considered valid, it must be logically coherent, containing no logical contradiction. In passing, this does not mean the theory itself can be easy to comprehend or not contain seeming paradoxes, and we shall return to this in later videos. So let's now look at the first of our presuppositions this week, and that is the idea of correspondence. Correspondence follows directly from the first axiom of coexistence, in that if a reality exists which is independent of ourselves, and this reality can be perceived and understood via our bodily senses, then not only does the theory have to meet the zeroth axiom, be completely coherent, it must also agree, and better still predict, the external reality under observation. We now have arrived at an ancient worldview of truth. For a theory to be true, it must be both coherent, meeting the zeroth axiom, and correspondent with reality, meeting the second axiom. The second axiom depends on the first, for the word reality presupposes the first axiom that reality coexists independent of our consciousness. So this just leaves our final presupposition of the four, and that is conservation. This axiom can be stated as follows. The laws of the universe are conserved through space and time. Why is this presupposition so important to the practice of science? Well, it is essential if we want to hold on to a strong version of the coherency principle of truth. What do I mean by this? Let us examine the following statement. Gravity is an attractive force which exists between matter, and gravity is a repulsive force which exists between matter. This statement is incoherent. We have just contradicted ourselves in the statement, and so it is contravening the zeroth axiom. Now examine this modification. Gravity is an attractive force which exists between matter at the present time, and gravity is a repulsive force which exists between matter in a million years' time. I have modified the statement so that the differing properties of gravity are now separated by the progression of time, and in doing so, my statement no longer contravenes the zeroth axiom. The reason is because the two statements are referring to two different universes, separated only by time, and so in principle, both could be true. Yet the consequences of such a thing complicates matters. For if the laws of the universe are not conserved through space and time, then we can no longer engage in the day-to-day practice of science, where we conduct experiments, because every theory will only correspond with reality at a particular moment in time. Therefore, we have no way of judging if any theory is closer to the truth than any other theory, because all are dependent on a particular space-time location. On a more practical level, scientists frequently repeat experiments to ensure that the results they first obtained were the right ones. If I do an experiment 10 times and I get the result X, then on the 11th time, if I get the result Y, I do not assume that laws governing this experiment suddenly changed. Rather, I assume that something has changed within the experiment, so on the 11th time, it did not give me a true representation of what I was measuring. Or perhaps the 11th experiment is the correct one and the other 10 for some reason are in error. Or finally, perhaps all the experiments are in error. However, now I must address one more very important issue. What constitutes a law of the universe? There is not an obvious answer to this question, as my next example will show. Imagine you live in a universe where you are the only person that exists, and the only other things that exist are billiard balls. Furthermore, there are no forces in this universe, no gravitational, electromagnetic, or electrostatic forces. As you watch the billiard balls, some are at rest relative to you, while others are moving. The billiard balls' motions are such that none of them ever collide with any of the others. What do you conclude from the observations you make on this universe? Well, firstly, you will notice that all the billiard balls, which have a velocity relative to yourself, maintain this velocity. The velocity never changes. Furthermore, those billiard balls which are stationary also remain forever stationary. If you were to develop a fundamental principle from these observations, a principle or law which is coherent and correspondent with your reality, you would come up with the following. A body will remain at rest or in a constant state of motion in a straight line. I shall call this law A. Now let us imagine that suddenly all the forces of the universe suddenly return to our imaginary one. Let us also imagine that our imaginary billiard balls suddenly possess electric charge. Now as we watch, we see two positively charged billiard balls move close to one another. As they do this, we notice that their directions begin to deviate from a straight line as they repel each other. Now we must modify our law, for it no longer corresponds to the reality we observe. Our modified law reads, a body will remain at rest or in a constant state of motion in a straight line unless it is acted upon by an external force. This is actually known as Newton's first law of motion. Now here is the interesting bit. If I apply the third axiom, the laws of the universe are conserved through space and time, with respect to what I first called law A, a body will remain at rest or in a constant state of motion in a straight line, and I live in a reality which is like our own universe, then it appears as if the axiom does not hold, because law A is not conserved. The motion of particles do change with time. However, the problem is not with the third axiom, but with law A. Law A has failed because it stated that an entity, velocity, in our universe is always constant, when in fact this entity is under other laws which can alter it. Likewise, it is possible to imagine a universe where the gravitational constant is changing in some predictable way with time. In this universe, the statement, gravity is an attractive force which exists between matter at the present time, and gravity is a repulsive force which exists between matter in a million years' time, could not only be a coherent statement, but it could also be made without violating the third axiom. For in this universe, the law which is unchanging is the law which governs the value of the gravitational constant at any given time, and not the gravitational constant itself. Yet notice one important detail about this modification I have made to our present discussion. While my universe, which has a gravitational constant that changes in a predictable way, can still be made to fit the third axiom, the description of this universe is more complicated. So we have paid a price. There is also a limit to how far we can take this. The more elements that can undergo change, the more complex our model for the universe will be. If nothing was repeatable and no law could be found that was constant through space and time, then we would be truly unable to develop any coherent model of the universe, and the practice of science would be impossible. Now, what is really fascinating about the conservation assumption is just how strong it turned out to be in terms of the fundamental constants of the universe. Probably the most mind-blowing example of the conservation principle was discovered by Einstein early in the 20th century, when he correctly realized the implications of what it would mean for the propagation of light to be constant independent of your reference frame. To briefly explain, a reference frame refers to your relative motion in relation to other objects in the universe. Galileo had already shown that the results of experiments appeared not to change in non-accelerating reference frames. In other words, if you were in a bus travelling at a constant speed with no windows on a perfectly smooth road, there is no experiment you can do on the bus that would indicate you were in motion relative to the Earth. While this was all well and good, general observations appeared to agree with Newtonian relativity in that if you were on a train going at 70 kilometers an hour and you were pushing a trolley along the aisle at 2 kilometers per hour, then the trolley relative to the track would be 72 kilometers per hour. Before some famous experiments were performed on light early in the 20th century, it was thought that the speed of light would also change relative to the motion of an object. Returning to our train example, if you were on a very fast train travelling at half the speed of light and you shone a torch in the back carriage pointing to the front carriage, then the speed of light relative to the track you would think would be 1.5 times the speed of light in the train. However, Einstein realized that if this was the case, then it would be that the laws of the universe would not be conserved in every reference frame. This is a major issue because the speed of light, as described by Maxwell's famous equations, was dependent on two fundamental constants, known as the permeability and permittivity of free space. Assuming these fundamental constants were conserved independent of reference frame meant that the propagation of electromagnetic radiation must also be the same in every reference frame. In order for this to be true, it meant that as an object approaches the speed of light, it must experience a different passage of time and also a change in spatial dimensions along its direction of travel in relation to the stationary observer. From these incredible insights, we came to understand that our universe is really a four-dimensional space-time architecture, with very fast motion changing the way an object travels through four-dimensional space-time. I shall return to a further implication of the special theory of relativity in a later thought video. When all is said and done, it turned out that the fourth axiom of conservation had much deeper implications on our models of how our universe operates than we could ever have imagined when it was first thought about by our early scientific forebears. Okay, so that is my thought video for this week. In the meantime, if you like this video, please do hit the like key, and if you want to see more of my content, then please do subscribe to my channel by hitting the subscribe button and the bell notification key below. Until next time, I hope your body and mind are in a good place, and bye for now.